Hey folks, we're about to start another episode of Ask Us Anything about electrochemistry. But before we begin, because we have some extra time, there are a few things I'd like to go over first. While we're waiting for the live stream to start, type your question into the chat. The sooner we get your question, the sooner we'll be able to answer it when the live stream starts. We usually try to answer questions in the order that we receive them, but it's definitely possible that we get so many questions that when your question comes up, we're out of time. If you are a Tier 1 or a Tier 2 YouTube member, you do get priority in us answering your question. You also have the opportunity to join us on the stream to either share slides or talk to us in person about your specific electrochemistry research questions. If you are a Tier 1 or Tier 2 member on our YouTube channel, you will find in the community post the link and password to join us on our broadcasting platform. We get a lot of questions about electrochemistry, whether it's through our YouTube comments, webinars, email, phone conversations. We get lots of questions from people about electrochemistry. And sometimes responding to a YouTube comment or trying to describe a cyclic voltammogram over the phone isn't always the easiest way to teach or describe electrochemistry. That's why we created this live stream. In the Ask Us Anything About Electrochemistry live stream, you can ask us any questions you have about electrochemistry, and we can use better tools and take more time to describe some of these electrochemical processes to help you with your research and understanding of electrochemistry. Now, in our time of doing this live stream, we've observed that if you ask a very, very specific question, we might not be able to answer it. It'll be a little bit too specific for us. On the other side, if you ask a very broad question and you're interested in just a very broad understanding of cyclic voltammetry, we have separate tools, we have other resources to help you. So we do have a YouTube video on cyclic voltammetry, an introduction to the subject. And if you're interested in more of a long-form course on, say, electrochemical impedance spectroscopy, we have a 5-part EIS webinar series for our Tier 2 YouTube members that you can access at any time. Now, if you weren't aware, Pine Research Instrumentation is a company that produces a wide array of high-quality electrochemical research equipment, from potentiostats to electrodes, electrochemical rotators, cells, different types of accessories. Pine Research has been supporting electrochemistry research and teaching for decades. Recently, we have developed new electrochemical simulation software called Aftermath Live. Aftermath Live is an online streaming platform where you can simulate popular electrochemical techniques like cyclic voltammetry. It's a powerful research tool, as you might simulate a cyclic voltammogram to support an electrochemical mechanism for your redox reaction that you're studying. But Aftermath Live and cyclic voltammetry simulation is also a very powerful tool when it comes to just learning electrochemistry. In fact, in previous episodes of the live stream, we have used Aftermath Live and our simulation software to answer some of the questions that you have. If you are watching this on YouTube, you can get a 10% discount on your first month of the basic and research editions of Aftermath Live by using the coupon code PINEYouTube10 when you're at checkout. Aftermath Live is a powerful tool and you can cancel your subscription at any time. Go to aftermathlive.com to check it out. Link is in the description below. Our live streams are normally on Fridays from 1 to 3 p.m. They normally last about 2 hours, sometimes a little bit more, sometimes a little bit less. If you miss the live stream, you'll always be able to watch it on our YouTube channel, and in the description we put timestamps for every question that was asked. This way you can look through the description and find the questions that are most relevant to your research and then watch those at your leisure. Also, we apologize in advance if we mispronounce your name. If on a YouTube channel you can put anything you want as a name. It could be a Pokemon, it could be a string of numbers. But if we call you out and we accidentally mispronounce your name, we apologize in advance. Lastly, please do not spam the chat. We've had numerous instances of people either talking about inappropriate things or constantly filling the chat up with some kind of spam. We will remove you if you do that. Let's keep the chat very clean and just talk about electrochemistry. Sometimes it takes a while before we're able to answer your question. So if you keep typing your question into the chat and spam the chat, then we will remove you from the chat. But if it's been a while and we may have forgotten about your question, one message as a gentle reminder is all that's required. All right, I think that's all of the housekeeping things. Now, let's start the live stream. All right, hello everybody.
Hello and welcome. We are live streaming, streaming live.
I scream, you scream, we all scream for live stream.
I stream, you stream.
I scream, you scream.
I don't want to scream because
it's for live stream, but
yeah,
you want to scream for live stream.
If you scream, it's going to distort the audio and everyone's going to leave.
That's true.
It's really, if we scream, these mics are very sophisticated audio equipment, right? If I scream, it's going to be very uncomfortable for your ears. I wouldn't do that to you. Alex might do that to you, but I won't. I won't do that.
I did make a video where I screamed once. It's hard.
Wait, which one? It was one of the funny ones?
I haven't.
Was it not? Was it something else?
It's an unreleased Aftermath live promotion video. I never put it out.
Does it just saturate the audio? Like, what does it do?
No.
Does it sound terrible?
Well, here's the thing. If you actually yell, so sometimes we want to be like, ah, as if we're yelling, but it doesn't sound like that when you actually have to actually yell into a microphone for it to sound like you're actually yelling. So
yeah, because you can't fake a yell. You can do like the whisper yell, like the right, that kind of sounds like yelling, but it's not. I mean,
yeah,
we're digressing a little here.
Yeah,
but that's just how we start. That's how we start the live stream, with a little bit of lightheartedness.
Yes. So it looks like we've already gotten quite a few questions coming in.
Yeah, we really should get to it.
So yeah, we can start getting to them.
There are a lot of them. And actually what I'm going to do first is I'm going to try to answer 2 questions at once, because AudioFile asked how to calculate and plot a Tafel plot for HER. And then we had a saved question from earlier in the week from Dooley's, who had asked this question. I'm wondering if you could do an example of foot of wave analysis for a compound like ferrocene. From what I understand, you can use the kinetic region of a CV curve to determine values for the symmetry factor in the exchange current density by plotting Tafel plot for only the kinetic current obtained at the foot of the wave. All right, so I can try to answer both of these questions at once. And the fun part is that I don't have ferrocene or HER data, so you're welcome. But what I do have is some CV data that could effectively be either, let's just say. Hopefully it will show you how these processes work. I'm going to share my whole screen. It might be trippy for a second. Okay. So what I have here is ruthenium hexamine. So it's like the next best thing, in my opinion, to ferrocene. Ferrocene's like a perfect 1 electron, super well behaved and non-aqueous redox couple. Ruthenium hexamine works in aqueous, and it's like the next best thing, in my opinion. It's a little bit easier to work with as well when you don't have complicated lab equipment, which I don't have, like a full scale laboratory and acetonitrile and ferrocene to kind of go moisture-free, glove box, all the things, right? So Dooley's, you had asked about ferrocene, can't help you, but I got Ruhex, that's the next best thing. AudioFile, I don't have HER data, but I do have a set of voltammetry data here. So hopefully you'll get the gist of this, right? HER data would be kind of like the beginning part of a wave here, something like that. Now, to be clear, I'm going to make a Tafel plot. I'll kind of show you just a little bit of how this can be done. And to be clear, the foot of wave thing, we were looking at it just a little bit ago. I'm not 100% sure if there's more to it. There might be some more kinds of analyses that are specific to that FW or whatever, maybe it has an own acronym with itself anyway. My impression of your question, Dooley's, or to anyone who's looking at foot of wave stuff, is that it kind of looks at, for example, in this voltammogram, not all of these data are kinetic data. And to make a Tafel plot, you must have kinetic data. But what we do is we can say with some level of accuracy, let's just, I don't know what level, but where the current is flat, and then it's like too many points here. I'll just kind of, where the current is flat and then it starts to go up exponentially. That's roughly the kinetic response. That's roughly kinetic data. That's dictated mostly by the Butler-Volmer equation. And so the foot of wave is the foot where the wave starts, where the onset potential is. So whether you're talking about the reduction or the oxidation part, it doesn't really matter. The point is that's my interpretation of what Dooley's was asking. And audiophile for you, it's a similar phenomenon. I'm looking at where the current starts to shoot up or down exponentially, thus indicating Butler-Volmer kinetic type behavior. So what I'll do is I'll make a Tafel plot from a voltammogram, which is the thing I always say not to do. So here we go. First, I'm going to copy this just because this is, you can see this is like a bunch of CVs all at once. I'm going to try to just isolate one trace here. Let's see. I think the sixth segment probably is good. Let's assume I'm going to get rid of the rest of these. Just keep one. All right. So what I'm doing here to sort of isolate foot of wave is I'm gonna select. I'm gonna get rid of some points just to get rid of some of the unnecessary data that I don't really care about as far as it relates to this analysis. So try to get rid of the beginning, and I'm gonna get rid of like some of the points up until the peak here. So it's somewhat arbitrary, to be honest. A real analysis might be a little more thorough. I'm just gonna get rid of these points. So here's like my isolated foot of wave. This is like the onset potential where there's an exponential increase. So that's what I'm going to be doing. Now, a Tafel plot, I always think about the Tafel slope when I'm trying to figure out what the plot ought to be. And the slope is usually expressed in something like millivolts per decade. So that's a y over x. So that means that millivolts or potential needs to be on the y-axis, and decade or decade of current needs to be on the x-axis. So the first thing that I do, at least in our software, is I'm going to do a swap of the axes. I'm going to replace the trace. So all I'm doing is swapping x and y. All right. So now potential's on the y-axis, current's on the x-axis. And now for it to be Tafel, I have to take the log of the x-axis. That's the last transformation I'm going to do. So you can see here I have Tafel log x. I'm going to do it on the x data, and I'm going to do that. And so here's my Tafel plot. You can see there's a discontinuity because the current passed through zero. It's just consequential of this. This is not like the best data to be doing this with. I just wanted to give you an example anyway. For your case, you might subtract the background so it's all above zero, and so you don't have this discontinuity. In any case, the procedure, hopefully is understandable, even though the data aren't maybe the most ideal for doing this per se. But really all we're doing now is getting a slope. Okay. And forget about the units. It's millivolts per decade because current, the logarithm of current is a unitless quantity. So we say decades of current, but it's technically unitless. So it's millivolts per decade. Now, this is the Tafel plot, and then this slope is the Tafel slope. So the question is more, where do I take the Tafel slope, which is a question I do get a good amount as well. The typical number is 120 millivolts per decade, right? That's like the number per se that is indicative of a 0.5 alpha value of perfect symmetry, as well as one electron transfer. And so sometimes what you're doing is exactly what I just did here, which actually happens to be exactly 120. It's perfect here if I set these limits. So I could say, well, these are the limits. Now, again, take aside the data I'm showing you right now may not be the perfect data. I just have a voltammogram that I've from my past taken. It's probably not the perfect data to be doing Tafel analysis with per se. So this specific analysis might not matter. Apply it to your data, for instance, right? But what I can do is I can look back at the data, for instance, and I took it on the oxidation side here. So like this trace. So you can see, for instance, if I'm trying to isolate kinetic data, foot of the wave, I could actually look and say, okay, well, probably I want to isolate it to about between like these two potentials, like 2 and 300, something like that, or maybe like minus 250 and 300, or minus something in this range. So what I can do is use this knowledge here and say, well, these potentials are roughly where I would say the kinetic information is happening, like 225 to 300, minus 225 to 300. So what I can do is, now it's on the y-axis, so 225. So I'm going to have to come below because of the discontinuity here, but let's just say 250, right? So I can move this to, this is 250 where my mouse is. So if I, in this range here would be where I'd start. And then 300 is about where it is now. All right. So anyway, let's just say this is where I take my Tafel plot, because those are the potentials at which I'm, wanting to apply it. And it's like 90 millivolts per decade. So that would give me information about the symmetry factor or the number of electrons transferred or something like that. And just as a refresher here, I guess, which the last thing that I'll show is, I'll pull up this webinar here. I want it to be this one. So this is my webinar on RRDE and Tafel. And so the slide I want to show is just the calculation of the Tafel slope and the parts that come into it. So this is the Tafel slope right here, right? And so alpha NF is in the bottom. And so essentially for 120 millivolts per decade, which is this number here, 118, 120, that assumes 0.5 and 1. So if it's less than 120, it means that N is greater than 1, or alpha is greater than or less than 0.5. So again, you just could basically do some very simple algebra here in mathematics and say, okay, well, my Tafel slope I got was 90 instead of 120. So that means that alpha is something other than 0.5, or N is something other than 1. For whatever I'm studying, right? Or some combination of both of those. But that was the other part of Dooley's question, is that how do I sort of extract or get to that parameter from the Tafel slope? And this is basically how. So that is what I will say about that. Hopefully that kind of addresses both folks' questions there about making a Tafel plot and getting those analyses for you. So.
All right, very good. Kind of moving forward with some of the questions that are coming in. Let's see. There's a question from Anindita. I'm trying to prepare working electrode with Toray paper. Want to know how to prepare the electrode, drop casting the catalyst onto paper. And actually, FCB has described part of that.
Yeah. So this is, so FCB has given some answers here. Prepared catalyst ink by catalyst, I assume sort of massing or measuring catalyst solvent in a binder like Nafion, sonicate the solution, cut the carbon paper, and load the ink uniformly and dry. You use IPA, isopropanol, or a mixture of IPA and water. That's right. Depends on different procedures have different mixes here. Mix with Nafion, so it can be homogeneous. Small tips is when you load in catalyst, it can't be flooded. And so Anindita had replied, how to keep the ink uniform, any tips? Because later you have to measure the area. All right, so I can talk about this a little bit. Loading up on Toray paper to make like an MEA. So to make your ink, it is as FCB described. Thank you for that, filling that in. Yeah, you're usually going to have a solvent of water or isopropanol or some mixture of them, sometimes 50-50. It kind of, it varies, I guess. Carbon is somewhat hydrophobic, so it does help to cut your ink with some alcohol. It helps it soak in. The uniformity comes from a couple of things. Oddly enough, it has been observed. I'm not sure if I fully understood why this is the case, but it does seem to be the case. Sonicating it in cold temperatures sometimes helps. So one of the things that you can try, Anindita, is you have like a sonicator. Usually, it's like the tub, and it has a knob on the front that starts the zzz sonication, right? Add ice cubes into the water. Get it cold. Sometimes that helps make your ink uniform. I'm not exactly sure why, but it does seem to work for some materials. Again, your ink will be something that you have to know all of the amounts that are in there, exactly how many milliliters of solvent, how many milligrams of your platinum bicarbonate or whatever you're using. So you know the amount that's there, right? And then you're going to either do it by dropping certain amounts of the solution onto your paper and letting it dry. And then sometimes you mask before and after, so you can do it that way. Alternatively, I use quite literally paint brushes. So I would take like art paint brushes, dip them into the ink. After it's been sonicated, you can stir it, you can swish it around, and make sure that it's relatively uniform, and then paint onto the Toray paper. You're probably going to need to do this a couple of times. So you're going to paint it onto the paper. Again, there's a flooding thing that FCB talked about. So don't soak it so much, you'll reach a limit here. But what you're going to do is you can sort of paint it on there, let it dry. Some people cook it in an oven. Some people cook it in an oven with nitrogen. Too hot of a temperature, for instance, with under oxygen can sometimes burn off the carbon. It depends how hot it gets. Sometimes it's only like 50 to 80 C is all you need, but just evaporate the solvent, right? You can do loads of this. So it's like mass the Toray paper, paint it on, dry it, mass it again. Now you know how many milligrams you've added, and you know the composition of your, well, you can assume the solvent's all gone. So actually the mass that you've added is just whatever solids were in your ink, which is the platinum on carbon or whatever it is, right? So you know how many milligrams you have of that. You can do it again because you're trying to get some loading. You're trying to get like 25 milligrams per square centimeter, whatever, right? So just calculate what's the surface area, how many milligrams difference did I add? Paint it again, dry it, mass it until you get roughly the loading that you want. So sometimes it takes 3 or 4, sometimes 2, I don't know, of those procedures to get the loading that you want. And by doing that, a lot of times, because Toray paper is pretty porous, you get it in the pores and it will behave a little better as a catalyst, because the gas diffusion layer means the gas will get into the pores of the carbon paper, and the catalyst is in all of those pores also, because the solvent, if it's not too hydrophobic, if the solvent can get in, the catalyst will dry in the pores, and then it's everywhere. It connects pretty well. And so those are sort of just some general advice, I guess I'd give you on that. Be very precise if you can in the measurement of your ink and in the massing of your paper before and after. And FCB also had a good point about cutting it. So you're going to cut. You have 2 options. You can take a big piece of paper and just slather the whole thing in catalyst and mass it or whatever. Sometimes that's helpful because you'll get a lot of it, and then you can cut a little square out afterwards. And usually that square, whatever size the square, that's your catalyst. The problem with that sometimes is that how homogeneous is the loading at all points in this big piece of paper. Whereas sometimes you can cut the square first, and then you paint that square, and it's smaller usually, or it's controlled. And so you get the edges and everything, but basically you'll have more even spread of your catalyst on that square of paper. And that might be better. Just again, be careful as well when you like handle it. 'Cause like your gloves, you could break the carbon, or your gloves will, smudge some of the ink. So there's just some things to kind of be aware of. Some of this is like an arts and crafts project. So you might need to have some trial and error, let's just say, as you figure this out. But hopefully that's a decent overview of this process for you, Anindita. And if you have any follow-up, please let us know.
Nice.
You should talk.
Yeah. FCB has a question about how to calculate the turnover number, and I think it's some kind of efficiency.
Yeah, what's
SE.
the S efficiency?
I don't know the S. I think you may be referring to like a Faradaic efficiency,
Something like that.
but you're doing a photocatalytic reduction of CO2 to produce carbon monoxide and hydrogen. You do GCMS using a 1 milliliter syringe, and you're just trying to calculate how much CO and hydrogen you're generating. So part of the answer to this is actually just in mass spec. So the way that this is usually done, not that I have a lot of experience on this, but generally speaking, your mass spec has some data that looks a little bit like this. You got lots and lots of lines. I'm just kind of making up some stuff, different lines of things. Maybe you have doublets and triplets of stuff, but you have a mass over charge ratio, and then I believe the y-axis here is some level of absorbance. Because you have some type of counts basically as the ionized molecules are moving through the quadrupole and all that stuff. They're getting counted via some kind of detector based on the mass and the magnetic frequency. So to determine, here's the thing. This is kind of the frustrating part. Is what you need to do is you need to create a standard. So you need to develop you need to figure out a way to put some known quantity of CO, carbon monoxide, and some known quantity of hydrogen through your mass spec. So, through your mass spec. And what'll happen is, I don't know the exact numbers, but I guess this is, let's see, it's 12. Maybe you'll get something around like 30 something. Will be its mass to charge ratio, so something around in the 30s. Just carbon plus oxygen, and then
CO
whatever.
is 28.
28.
Yeah, I'm helping.
Oh, 28. Okay, 28. All right, so that was 28, and then
hydrogen's obviously.
This is 2.
Yeah, that one was easier.
Yeah. So this is 28.
Yeah, 12 plus 6.
You'll have something around here. It might not be exactly that, because if the charge of whatever the ion is not 1, then it'll be different than 28.
Yeah.
But you'll know where this is coming out of. And if you create a standard that's just a low concentration, a low pressure of CO in a 1 milliliter syringe, then you'll know, like, oh, I'm going to get, this spike around 28. And I know that this corresponds to, I don't know, some ppm or a known mass. You'll know the number of moles of this, because you'll have the volume, and you'll know the absorbance, and you know how much is in there. So you'll be able to determine the moles of the standard. Then when you have your mixture of CO and hydrogen, because hydrogen will be here, hydrogen will probably be somewhere here. When you have your mixture of H2 and CO, this is in your syringe. This is a little plunger. And then when you put it in, you're going to get like a different value, a different absorbance. It'll be the same like 28, and it'll be at 2. But by using a standard to determine how much it is, you may have to have multiple standards. You may need 3 or 4 different standards of CO and H2 to determine, I can create a calibration curve. And what that is, just very, very generally, if I just make a new one of these, what you can do is you'll be able to create a little curve and do a linear regression. So you'll have your concentration on the x-axis. You'll have your absorbance from your mass spec on the y-axis, and you'll get a nice line because you'll have several data points from your standard. These are all coming from your standard. And this line will fit a y equals mx plus b. And something, B should be 0, right? At 0 concentration, there should be, zero absorbance. But you'll have one for CO, and you'll have one for hydrogen. And when you do your experiment where you're doing photocatalytic reduction of CO2 and you measure CO, you'll get a data point that falls somewhere along this line. And then when you take this absorbance, and then plug it, you'll plug the absorbance in, because you know what the mass, what the y coordinate is. Then you can back calculate from the slope to figure out what your concentration is in moles. So this is how you ultimately determine, this is the general process for figuring out from a CO2 reduction reaction to CO and hydrogen, how many moles are you actually generating in this 1 milliliter syringe. So it's just a little bit of math, a little bit of just some dimensional analysis, because you'll have a volume, you'll have a mass, you'll have moles, you'll have absorbance. So you just have to do a little bit of that to ultimately get this. The other important thing to keep in mind is that CO2 to CO is a 2-electron transfer process. So when it comes to determining the efficiency, if you will, in your photocatalytic reaction, you're going to have probably some time. Maybe this is like a chrono amperometry or chronopotentiometry experiment. You have current. And so, nothing, light turns on, and then you get something, blah, 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 blah. And then you turn the light off, and you'll have this charge that's here. The integral of this charge, the area under the curve, will give you coulombs of charge. I never spelled coulombs right. Yeah, coulombs, something like that. And then you can use Faraday's constant to convert coulombs to moles. But you'll need to keep in mind the fact that it took 2 electrons for every mole of CO2 to create a mole of CO. So that is involved when you're trying to determine, say, your Faradaic efficiency for CO2 to CO. Because not all, if you look at this charge and you're like, oh, I generated so many moles of CO from this, keeping in mind it's a 2-electron transfer process, but then your mass spec gives you a different amount of moles, then the ratio of mass spec moles versus echem moles is going to be your efficiency. That's going to be whatever your percent efficiency is, because this is what you actually got. This is what you actually measured. But this is the theoretical, fundamentally, this is the coulombs of charge that were passed in the photoelectrochemical reaction. That's the theoretical maximum, and then but the mass spec is what you actually got out. So I hope that was helpful. That I think is what you were specifically asking. But if you have further questions or comments, please let me know.
Okay. So next, Kuldeep asked, "What is a Daniell cell?" And I assume you mean Daniell cell, or Daniell. I'm not sure what the pronunciation of it. It's like, was it DENEIELL?
It almost looks like a Daniell cell.
Yeah, like a Daniell cell. Daniell cell.
Yeah.
So I believe what you're talking about is basically it's like the zinc copper electrolytic cell, the pretty famous common one here. So that's what I'll describe very briefly, and I assume that's what you're talking about. But it basically is effectively this, where you have two compartments separate. Okay, and what you have is a salt bridge in between the two, which is where electrolyte can go. In one side, you have copper sulfate electrolyte. In the other side, you have zinc sulfate. On one side, you have, I should have drawn different colors for those. That's all right.
Yeah, it's all good.
It's not like zinc or copper are actually green. I'm just trying to make it visually different here. This one will be a zinc metal, Z, and I'll use red over here because we all know copper is very red. It's not red. I guess it's close to copper color. Anyway, you put a copper metal here, okay, and we connect these to an external circuit or potentiostat or voltmeter or something like that. There's an electrolytic reaction that occurs. So basically, we have two reactions. Make sure I get these right here. Copper is 0.337, right? Okay. So what we have is copper 2 plus 2 electrons goes to copper like metal, and the E0 for this is let's just say 0.34 volts. And then we have a zinc reaction that is zinc. Is it like minus 0.7? Was it minus 0.7 something? I guess I'll find it.
Yeah.
Sorry, I'm like
Yeah, something
asking
like
you.
that.
You're like, you're doing other things. All right. It's
Yeah, it was
minus.
minus 0.7.
Yeah, minus 0.76. Got it. Okay. Where am I at here? Here. Whoops. No, wrong one. This one. So on this side, we have zinc. We have zinc 2 plus 2 electrons goes to zinc metal. Okay, I'm drawing them both as reductions on purpose here. I'll explain. In this E0 is minus 0.76 volts. That's a 7. That's a terrible looking 7. There we go. All right. So what we have here are two reactions who have different potentials. Okay. They're both written as reductions. So what this means is that one of them will happen as an oxidation, which is the zinc. Okay. So what happens is that this is the potential of this as a reduction, which means that the opposite of it is the if the let me say this the right way. The E cell is equal to the cathode, which is where the reduction is happening, minus the potential of the anode, which is where the oxidation is happening. Okay. So what we can say here is that the E cell for this is the Daniell cell, is the cathode, which is where the reduction is happening. So this is the copper. So that's 0.34 minus a negative 0.76. What this means is that we have a positive voltage, right? And so that's 1.1 volts here. Okay, that's a 6. It looks like a cherry. 0.76. Right. So we have a positive voltage. What this means is that it's spontaneous. And so effectively, the zinc is going to go in this direction. It's going to go the other way. It's going to oxidize. So zinc metal is going to go off to be zinc ions. It's going to be more zinc 2 plus. It's going to basically, the zinc metal dissolves effectively, right? And copper plates. Copper 2 plus 2 plates onto the metal. So zinc dissolves, copper plates. This happens spontaneously. And we have 1.1 volts. So this is what the cell, and then the salt bridge is needed because these compartments are kept separately so that the copper and the zinc can happen sort of independently, but we have to have charge balance. And so what we have here, of course, is because this is oxidizing, electrons are going in this direction because the copper is reducing. So the copper 2 plus electrons are combining over here. So what we have to have is either movement of negative ions in the other direction or positive ions in this direction. And most probably it's the sulfate. So what happens is that sulfate ions will move over the salt bridge. It's usually like just a piece of cloth of some kind, anything that can wick electrolyte. But basically sulfate ions, SO4 2 minus, sorry, my running out of space to write here. But the sulfate ions will move from the copper solution to the zinc solution to maintain charge balance. And that's what happens. So that's like the very simple galvanic, not electrolytic. It's galvanic. Electrolytic would mean it's not spontaneous. So it's a galvanic cell. It's spontaneous. It occurs. It has a voltage associated with it. You dissolve the zinc. You plate the copper. Everybody's happy. Next question. So that's it. Okay. So that's what the Daniell cell is, basically. And the next question here, I don't know what this means. I'll just get this out of the way. What is the electric potential of ZJ? I don't. Do you know what this is? I don't know what ZJ means.
No, I thought he was talking about what was the potential, which you said is 1.1 volt. I thought that was what he was asking.
That is?
But I don't know what they mean.
I don't. Yeah,
of
cold deep. I don't know if
ZJ.
that's something different. I'm not sure.
Yeah.
If you're talking about the Daniell cell, it's that I showed you how to calculate that potential. So I don't know what that means specifically, but yeah. So there you go. That's what that cell is. So.
The next question comes from Connor Broderick. Connor asks, why is it that sometimes adding a large volume of electrolyte leads to huge resistances in 3 electrode CVs of small molecules? For example, I've sometimes run CVs in 4 milliliters of 1 molar lithium OTF electrolyte and solution with 5 millimolar analyte, and I get such a high resistance you can't even get a current response, But if you drop the volume to 0.5 to 2 milliliters, it works perfectly fine. This is definitely unusual. It's normally the case, as you said, that it's not even the volume of electrolyte, but really the thing that affects solution resistance most of the time in a standard 3 electrode CV system is the distance, if you will. You're looking at the resistance between the reference and the working electrode. That's usually part of it. The fact that you're not able to get the experiment to run in some cases, I don't know if that has another implication about the geometry of your electrochemical cell. But generally speaking, it is the electrical contact between, like, the distance between the reference and the working electrode creates what we call uncompensated solution resistance. So if there's not that many ions between those two and it's very resistive, it's very hard for your experiment to happen. At the same time, your counter electrode has to drive current through the cell, and you may be running into a compliance voltage issue. So the fact that you go from 0.5 to 2 milliliters makes me feel like there's something going on in the cell. When you change the cell volume, the cell geometry is changing in some way. Um, that's kind of my, without any more information. I don't know
Well,
if there's
there was a
anything else.
follow-up that
Mhm.
he put a little later. He said, similarly, I've tried to cycle an
Mm,
LFP, lithium iron phosphate coated stainless mesh before to deintercalate it to make a lithium ion reference, but I get a
mhm.
similar massive spikes in resistance with my cell with a lithium counter shorted to both the counter and reference. Lithium counter shorted to both the counter. I got it. So lithium is the counter and the reference. And an
Okay.
LFP coated working. My coding isn't great, but
You
I
can.
can't even get current response on a CV with formula. Okay. So um, the main concept here to be aware of is that with battery electrodes, battery materials, and thinking through part of what Alex just said in terms of the distance between the reference and the working electrode, adding to uncompensated resistance. First of all, with battery materials, even with relatively concentrated electrolyte, the resistance is higher. The solvents you're using for battery electrodes um, add they have higher resistance than like water and stuff like that. So they have higher. The second is that I don't know how well I can describe like why theoretically, but battery electrodes require proximity and pressure. If you are trying to do 3 electrode experiments with lithium salts and lithium batteries, you will struggle heavily, as you seem to be, mentioning it as part of your questions. Whether your first set of questions is uh, related to the second here, a continuation kind of, but effectively you're saying a large volume of electrolyte leads to huge resistances because battery electrodes are not meant to be performed this way. There's a reason why batteries are like tight wound cylindrical cells or pressed coin cells or prismatic cells that are like pressed layers of sheets together. The electrolyte is soaked in there and they're pressed together, and that's a form factor that's very tight in volume because batteries don't work otherwise. The diffusional paths need to be small as possible. The membranes and the separators need to be thin. The electrolyte needs to be concentrated, and only then do they really work. So your resistances become so high if you just try dunking them into a 3 electrode configuration or a 2 electrode configuration with any appreciable amount of volume. The resistance is so high you basically won't get any intercalation or deintercalation. The resistance will be so high, your IR drop is so massive it eats up everything. You basically don't get what you're after. You're applying 3 volts, but it's really like 1 volt because you're eating 2 volts from IR drop or whatever. I'm making up these numbers
Mhm.
obviously on the spot here, but proximity and pressure is required. I did, when I was in graduate school, some tests where I had to use like a liquid setup just similar to this, with a lithium metal as the reference or the counter or whatever. And I had to do a thing where I literally wrapped and physically hugged the electrode, the lithium, because lithium metal, if you've used it, it's very like not sticky. It's malleable. It bends and folds and everything. It's not like a piece of steel. It's very flexible. So I had like my working electrode, and I, instead of dunking like lithium metal and my working electrode in solution, I took the lithium metal and I wrapped it around like physically around the working electrode. So it was like touching as close as possible. Obviously not really, there was a membrane in between, like a piece of plastic or cell guard or something. But having them be physically close, and even then it didn't work that well. It worked well for what I was doing, my purposes. But the proximity and the pressure is just necessary in batteries. It just doesn't work without it. I'm guessing it has a lot to do with what I said, or what some of the things you said about ion drop and the diffusional path length and things like that. But you need to really think about proximity and pressure when you're thinking about these battery materials. You just have to go down that assumption that a typical 3 electrode setup is not likely going to be very fruitful for you. So Connor, please follow up if you want any more specifics about your setup and everything. I'm happy to talk about it some more. I have a good amount of experience with batteries, but that's my, I don't know, overview, I guess, high level, from above overview of what you might be kind of having trouble with here, I guess. So let's see. Where are we at next?
We have a question from Naresh. I don't, just kind of going in order.
Yeah.
I don't know if we can really answer this well, but Naresh is asking how to interpret EIS in a manuscript, any main point, etc. I mean, it depends on what your EIS data is, and what you're trying to describe.
It sounds like you're trying to publish a paper, and either your advisor, or if you took a crack at the submission and you got a review, someone said, add impedance data to you. And you're like, okay, I have to do that. So how do I interpret it to put into my manuscript? The simplest answer is do impedance at a few different potentials. If you have a specific reaction you're studying, set a baseline near the E0 or at an overpotential of that reaction and get impedance. And look for some semicircles, look for some diffusional behavior, look for things like that. Semicircles have widths. The width of the semicircle is proportionate to charge transfer resistance. So what you can at least do is, under a few different conditions, try to extract values of charge transfer resistance. And you can say things like the charge transfer resistance at this potential, or at this pressure, at this temperature, at this day, when I was feeling happy or feeling sad, whatever the correlation is, the charge transfer resistance was 100 ohms. And then when I decided to change the potential or change the temperature, my charge transfer resistance went down to 80 ohms. And so I have a correlation between the performance was better because the charge transfer resistance was lower. These are just some general examples, the kinds of things that, reviewers might be looking for in a manuscript, and ways that you can kind of use impedance on a very general level to enhance your manuscript, I would say. But really it is hard to answer beyond that, because it depends on what you're studying, what your data look like, what your system is, and everything.
So, time permitting, there will be some EIS data that we'll actually go over later in the live stream. Hopefully, if depends on how we do with questions, because people can submit some data to us and we can look at it and try to interpret it. So if you stick around, we're going to look at some sample data, and that might help you with figuring out how to interpret EIS data for your manuscript. Okay. All right. Moving along.
Power density.
Yeah. Mohammed is asking how to calculate power density through data of cyclic voltammetry. I have only V and I.
I can show you.
Yeah.
As a matter of fact, let me do that for you.
Mm-hmm.
I also have only V and I, as you can see right here. So for instance, this is a polarization curve. It's the same as a voltammogram, but I already swapped the axes. So current is on the y-axis, voltage is on the x-axis. It doesn't really matter. I've already pre-swapped these axes. This is, again, usually what you are getting power from, is potential and current, right? So you have E and I. Well, power is just the product of E times I. So at all points, what you can do is multiply E times I. So what I'll do is just that. I'm going to do, where is it? Product, right?
Multiplication.
No.
Oh,
I want
Oh, product XY.
Product XY. I can't. Oh, there it
There
is.
it is.
XY product.
Yeah.
I'm just blind.
XY product.
I'm
Yeah.
just blind is all it is.
Uh,
Okay. I don't want to replace the trace. I want to add it. I'm just going to add this trace. So what I'm doing is I'm keeping the x-axis. You could do it with either way, right? If you want the, usually you plot power with a polarization curve versus current. This is a common way that like fuel cells or electrolytic cells are, the plots are shown. If you want it the other way, you would just swap the axes, just put the potential on the x-axis. But what I'm doing is I'm creating a secondary y-axis against current. And so here we go right there. That's it. Now, this is easier said than done with this our software I'm showing you, because Aftermath is built in units. So for example, I told it to multiply x times y. X is milliamps, y is volts. Our software knows that the product of milliamps and volts is milliwatts. So there you go. This is the power axis right here. This is it. It's actually power versus current. It just kept, the x-axis. But at all points, it multiplied the xy of all of these points and gets you these new ones. And this is what you typically see with a polarization curve, is that there's a maximum and it's not always corresponding with where you'd expect it. So you're looking for where that maximum is. That's the max power. So at, whatever, this voltage point here and this current, I have a maximum, power, whatever. And then if you want power density, all you're doing is dividing this whole thing by some area unit. So you just change, I think it's just change units or something here. Like all you're doing is just dividing by y-axis. I guess I want the y-axis and area. I think I want to divide by it. Not angle, area. Let's see. I might not be doing this right. Yeah, I just changed it. That's not what I wanted to do. Oh. Yeah, that was changing the unit. That's not what I wanted to do. I'm not using this right. Anyway, the point is you would, it should be density, current density. So one way to do this, I'll do this a different way. Let me just do this a different way. On X data, I'm changing this to current density. I'm not sure. Oh, because I have these. This is not a good example. I'm going to stop doing this. I've monkeyed with this trace before, and anyway, the axis is like already changed. This is from something else. So what I'm showing you is kind of a pain. Oh, anyway, the point is the power density. The only difference between power and power density is you divide by the area, and that wasn't the best example plot to be doing that with. So my apologies, but the power calculation was correct. So it's just multiplying E times I at each point and then plotting it against the x-axis. That's the power density, or the power right there. So it's quite a simple calculation.
Okay. All right. Great. Just moving through. We have a question from on LinkedIn from Yogi. He's asking, "Hi, Pine Smart people. I'm working on corrosion-resistant ceramic coatings while measuring open circuit potential and Ecorr from Tafel have large differences around 150 to 200 millivolts, even after giving stabilization time of 1 hour. What will be the probable reason for this, or suggest the standard procedure to do the electrochemical measurements? So why is it the case that the open circuit potential and the Ecorr have very big different values? We had a question like this some time ago.
Yeah, there was the one about the difference between the two.
Yeah, and I'm not. It's really weird when I go to like the PalmSense website. Like they say that the open circuit potential and Ecorr are the same things, and yet at the same time, it's like, well, then why aren't they just called the same things? But some people disagree, because I think one person described it as the open circuit potential is the potential where no current passes. This is a point that you made. Like, why would they be the same thing? Because there's an Ecorr.
Yeah, it's a bit confusing, to be honest.
And then someone said that the open circuit potential is really the equilibrium potential, but the corrosion current, because it's corrosion, or the corrosion potential, because it's corrosion, is not technically at equilibrium because it's corroding.
Yeah.
So, so from that thought process, there's a part of me that feels like you won't have it's okay to have a difference between the open circuit potential and the Ecorr, um, because they kind of represent two different things.
Hmm.
The open circuit potential is when no current is passing through your electrochemical system. It's only a tiny current because you have to have a small current when you're making a measurement, but it's negligible um, considering the scale of things. But the corrosion potential, to my understanding, is the potential where corrosion is happening, and it's the result of doing Tafel analysis and kind of the kind of intersection between the two Tafel slopes for the anodic and the cathodic wave, or cathodic and anodic branch, I would say, of the current. So, so that's my kind of my understanding of the system and why you won't see why you won't necessarily see stabilization after 1 hour. But I'm trying to think if you're doing a Tafel analysis on a corrosion resistant ceramic, what would be the necessary electrochemical procedure? I think you still do a kind of like slow CV
Yeah,
LPR
slow scan
experiment.
away from OCP.
Yeah.
Yeah, yeah.
Like maybe OCP is stable, and then when you're doing your very, very slow scan, you're getting some currents. You're able to create one of the Tafel slopes, and then do it the other direction, you get the other Tafel slope.
Yeah.
And where those two Tafel slopes intersect may not be where the open circuit potential is. So that's my thought, but without knowing everything about your system, what's the reference electrode you're using, what's the solution itself, your counter electrode. It's hard to tell exactly, but that's just my thought.
But I think part of your, the point that you made before too was probably the heart of the answer, which is that we're accustomed to the OCP and Ecorr being the same, or we think about them being the same, but the Ecorr is the place where it's the corrosion potential. It doesn't necessarily, and there's an Ecorr associated with it.
Yeah.
It's not zero. It's not. I think practically what we have is the situation where we start at OCP, like with our potentiostat in our system, and we polarize positively and then we polarize negatively, and we get the Tafel plots just as you described with the slow scan kind of a thing. But there's nothing necessarily like fundamentally or thermodynamically that necessitates OCP and Ecorr being the same. I don't think that I think that was your point, right? Like
I think
I'm also in the
know
same
enough.
boat as you. Like we're not really. We tried
Yeah.
sort of like I tried kind of thinking this through, and it's like I'm not sure I know the theory perfectly well enough. I don't think either. But we're trying to
Yeah.
like wrap our heads around it, but they don't
Yeah.
necessarily have to be the same. Is the point? I don't think anyway.
It seems like that, and
Yeah.
and the kind of argument that people have that the corrosion, because corrosion is not at equilibrium, right? Like, because if it was at equilibrium, the thing would be corroded and it wouldn't change at infinite time, right? But the thing does corrode. It's very, very, very slow,
Yeah.
but it's technically not at equilibrium. It's because it would still continue to corrode in an enclosed system, sort of say.
Also, the system, it appears he's saying 3.5%.
Oh, okay.
3.5% brine with platinum counter and
Okay.
a coated 316 stainless steel working electrode.
Okay.
So the other thing is that, my friend, you're probably not going to get a lot of corrosion.
Oh.
Stainless steel does not corrode much at all. So I suspect, stainless steel is it's stainless. So part of the just difficulty of your test, and probably in general, is that you are up against a system and a working electrode that has a very high polarization resistance. It's by design, right? 316 stainless steel is tremendously resistive to corrosion. That's why it's called stainless steel. So that could be part of it, is obtaining the parameters, and the passivation layers that form on stainless steel happen pretty quickly with slight polarization. So there's also that added wrinkle as you start scanning away from open circuit potential, it's tricky. You're making Tafel plots, and how accurate are they? It's not really kinetic after a little while. You have passivation layers. That's like full diffusional capacitive kind of stuff. It's not kinetic. There's some gray area here. We all make Tafel plots with 200-300 millivolts of, scanning away from OCP, and it's like it's not kinetic data. So the Tafelization of the data is not maybe ideal. And especially with stainless steel and these kinds of materials, they make a passivation layer. They don't corrode very much. So there's not a lot of kinetics. Corrosion is kinetic. So, so some of that is just tricky. But I do think that fundamentally the main point is don't necessarily get hung up assuming OCP ought to be the same as Ecorr. I think some of eventually we're gonna figure this out. I think you and I at some point we'll wrap our head around a proper explanation for that.
Know what the difference is.
And I for now, all we can really do is just be honest and admit that I'm not 100% sure why, theory-wise or thermodynamically, why that's the case. But I believe that is a correct assessment. They don't necessarily have to be the same. So the fact that you have a few hundred, millivolts difference or whatever, I don't know that that's a bad thing. So I don't think it's an indication you're doing anything wrong per se, right? So I would take that as some amount of heart, right?
Yeah.
I don't think you ought to be necessarily concerned about that.
Would you also say that there may be some systems, as odd as it may sound, it can take over an hour for a system to stabilize?
Oh, easily.
Yeah. So even an hour.
Yeah.
As odd as it sounds.
Yeah, no, it is odd when you consider, as a comparison to like the platinum or a glassy carbon or a simple small disc electrode. Some of the reasons are because a lot of times with corrosion setups, you have like a plate of, a larger form factor maybe of electrode. And so when the surface area is larger, it can take a little while for it to stabilize. You can observe, for example, sometimes in LPR corrosion long-term experiments that the OCP drifts for like 45 minutes. It's just kind of like it's never flattening out. Like you're not doing anything. Like what's going on? Why won't it just and it's like it can be a passivation layer. Like the passivation layer thing is a real thing. It kind of forms and sometimes it grows a little bit, even though you're at open circuit. And it can take it's a frustrating thing. Corrosion testing, especially for stuff like stainless steel, I think, in other materials. Sometimes the materials that corrode really fast. Well, we don't really want to make pipes out of stuff that corrodes really fast, but for testing purposes, when it corrodes pretty readily, sometimes it makes testing a little easier, like electrochemically, because the kinetic, charge transfer process is there and you can study it because it's happening. And it's like the other stuff, it's like, well, it's not corroding. That's great, but it's hard to study because it doesn't corrode. Yeah. So it's like it's a catch-22 a bit, right?
Yeah, that's true.
So yeah, it certainly can take a while sometimes to stabilize. All right, let's see. There was some Daniell cell talking about, which we already went through.
There's a one from Pankaj. Yeah. Pankaj is asking, tell the basic experiment for analysis of heterogeneous electron transfer rate calculation.
Hey, this is right up your alley.
Yeah, we
didn't
literally
ask about about the exchange current density.
There's like I was speaking with Neil about this earlier this week. That actually we think that there are three methods.
Oh, you can talk about the trumpet plot.
Yeah, there are like three different ways you can calculate.
I still have to do this experiment. When I have this, I'll talk about it on a stream, or I'll do it. I'll do a webinar on it or something.
So there's generally three ways. So first off, we're talking about the determination of the heterogeneous rate constant, sometimes called K, and this shows up from the Butler-Volmer equation. I'm just going to say BV equation. And so this can come about from a few different ways. One thing you can do is EIS. If you have a traditional 3 electrode system and you have EIS where you're doing, especially if it's around the E naught. So if you do EIS around the E naught of your reaction, and let's say we just have A plus an electron goes to B, and it's reversible. And then you have Z real. And then you have negative Z imaginary. Oops, Z imaginary needs to go on the other side. Z imaginary. You get these Nyquist plots that look something like this. Well, this distance here is typically the RCT. And RCT is equal to, and if I get this
RT over
right,
NFI, right?
yeah, RT over NF I.
Yeah, I zero.
And this will be an I0, your exchange current density, if you're doing it at about the E naught. So if you can determine this from your Nyquist plot, you can then get this value, and then this is like,
Was that NFAKC?
yeah, it's like there's a concentration, there's an area, and then there's like K, something along
I think
those
it's
lines.
NFAKC. Yeah, so there might be an N in
Yeah,
there for number of electrons transferred. Or
yeah.
whatever, but anyway.
These two are like equivalent, but your
Yeah.
K comes out here. It's related to the exchange current density and the charge transfer resistance. So that is method 1 for determining K.
Yeah.
Now the other method, actually, hold on. I still have I still need that equation. That equation is still useful. Hold on. Lasso tool. The other method that is to do a rotating disk electrode experiment. So you can do RDE. And so in RDE, if your system, you should get these voltage versus current plots, and they may look something like this. And this is your, like, let's say this is 0, because this is a reduction reaction. So we have negative current. So within this region here is what we refer to as the kinetically limiting region. And data points, voltages around here, you can plot using the Kurecki-Levitt equation, which I think
If you don't have it, I have it.
do I have it? Here we go. Yeah, so here it is. So I'm just going to copy. I'm going to take this, and I'm just going to paste it up here so we can all see it. All right. So, okay. So this is I'm going to get rid of this for now. The Kurecki-Levitt equation, where 1 over the measured current is equal to 1 over the kinetic current plus 1 over the mass transport limiting current. We can use the data points along here in order to create this kind of plot. And what ends up happening is you'll then ultimately create a plot, because you're gonna vary the you'll be varying the rotation rate. So you'll have like a variety of different rotation rates, and you'll get these plots that look kind of like this. And this is rotation rate to the 1/2. And the intercept, what will end up happening is your intercept here, the y-axis intercept, is related to 1 over the kinetic current. So just like in the EIS example, you can use a rotating disk, which is very stable, within this region, to get this kinetic current. And then from the kinetic current, you can determine
Same equation as before.
Same equation as before. So, and then the last thing that I was talking to Neil recently this week about,
Yeah, I'm definitely doing this experiment at some point.
is let's delete all this chunk, is to actually do CV. And CV is the one that's probably the hardest, but ultimately, and all of these things need some level of like advanced equipment, as well as they need CV, some level of advanced equipment. Like you need a rotator, you need a potentiostat that can do EIS, but you also, for something like CV, you need fast scan rates. So what people do is, as you do a CV experiment at faster and faster scan rates, you'll notice that once you go to faster scan rates, you'll actually start to see deviation, peak splitting between your first and your return wave. And this is a function of the scan rate. Scan rate. Can't draw. Scan rate. So what people do is if you know everything else about your system, the concentration of your analyte, the diffusion coefficient, you can do what's called a trumpet plot, which measures scan rate versus the peak anodic and the peak cathodic difference. So you may, in the beginning, when the scan, when you have relatively slow scan rates, you're still always going to get like your 50 millivolt peak separation between these two. But at a certain point, once your scan rate is fast enough, you actually get this deviation because you're scanning on the level of the electron transfer of your system. So what you need to do, and this is hard, you need to simulate what does it look like. You can't calculate this directly, unfortunately, like you can with EIS.
It's empirical.
It's empirical. It's just based on simulating what this would look like for like a perfect K, K equal to 1. And then, oh, your data points are off. What if my K is this value or my K is this other value? Does this match well? Knowing, again, the diffusion coefficient's the same, the concentration is the same for your species. But you can estimate K using simulation software. So you need to use simulation software, which Pine has, that you can use to do this, called Aftermath Live. So that's the other way of doing this. So so yeah, that's how you would figure out the heterogeneous rate constant in a nutshell.
Pretty good.
That's it. Yes. Something I was actually looking on and working on this week.
I'm gonna make that trumpet plot. That's one of my plans. If we can scan fast enough, I have to find a
which is hard. You need to find a system.
The Ruhex is probably too fast. I might try.
Ruhex
I might try anyway and see what happens.
Yeah,
I might not ever separate.
Yeah,
do like 50 volts a second, and it's still just right on.
Yeah, and you gotta watch out for like double layer capacitance. I mean, double layer capacitance is not as big of a thing, but double layer capacitance will scale faster.
And IR drop will,
and the IR drop will also
compensate
increase
for IR drop in there too.
So compensating for IR drop is also important too. So that's another thing.
Yeah. Okay. There's talk about power density, energy density. I think we'll move past.
We're done with that. Yeah.
I see Connor. Connor had said you might coin cell case. Yeah, it might be better. Yeah, you send some email if you need to. Naresh was following up if it's diffusion controlled. How does it be in terms of RSWs? Okay. I can just show you in our software, I guess.
Yeah. And similarly, Muhammad is asking about like how to plot like simulation for EIS equivalent circuits. Now we don't have free software, but so I don't know if we can help you with that, but we can still show you how we use it in our software. I can show you
our software. So I mean, it's not exactly the same. I get it, but circuit simulation. So for example, the question, what was the person asked about Warburg or whatever else? So I'll build one and show you where they come into play. I guess that'd be helpful. So the typical Randles circuit is probably what you're most after here. I'll just use a plain Warburg just for simplicity. Let's make this the same number. So this would be like a Warburg, Randles circuit. So we have a leading resistor for the uncompensated resistance or the series resistance. We have a resistor and a CPE or a capacitor in parallel, as well as a Warburg element in series with the resistor. Just give it some dummy name for now. Okay, and we'll just simulate this. I'll show you where they come into play. So what EIS looks like, it usually looks something like this. Pretty standard kind of a shape of a plot. The R1 is the x-axis intercept. So R1 is 1,000 right now. You can see if I make it smaller, the whole thing moves left or right. So that the uncompensated resistance shows up as the x-intercept of the whole plot, basically, on the Nyquist plot, on the right plot here. You can see how changing that moves that around. The charge transfer resistance is the width of the semicircle. So as R2, it's 1,000 right now. If I make this bigger, the semicircle gets bigger. If I make it smaller, the semicircle gets smaller. So that's proportionate to the charge transfer resistance. And then the Warburg sorry, I'll go to the C. So the CPE right now is a constant phase element. I have it alpha as 1 for a ideal capacitor. If it's less than 1, the semicircle looks squashed. See, the semicircle kind of is like not fully semicircle, or it's a perfect semicircle. So that's what that does. And the changing of the value of the capacitor in the case of a Randles element changes the sharpness between the semicircle and the Warburg part. So you can see that the it changes on the Bode plot. It changes where the blue dip, where the phase angle peak, if you will, appears. But on the Nyquist plot, more sharply, it shows more clearly. It shows how sharp the transition, if you will, between the charge transfer resistance part and the Warburg part is. When you have something like this, a lot of times it's like the diffusion and the charge transfer process are kind of blended. And then something like this, they're very distinct. It just means they have different time scales, very different time scales. And then the Warburg is, as it gets bigger, the tail gets bigger. I'll try to, it's already zooming. Okay. As the Warburg constant coefficient gets bigger, the tail, it's more diffusion dominated. As the Warburg constant is smaller, there's less diffusion domination, basically. And so that's how far that extends out. And this is a infinite plane Warburg, very strictly here. I'm not accounting for non-idealities or anything else. And so it's a 45-degree angle, which is not always the case in real data, but for a typical, perfect Randles circuit, this is where that comes into play, where that shows up.
All right. That was that. So yeah,
that's the Randles stuff. That's RS, RCT, and W in semicircles. So
yes.
Hopefully that kind of addresses some of those standard sorts of things, I guess. So
yeah. So there's a question from Saktipada. Again, sorry for mispronunciation of names. For ammonia oxidation, boron doped diamond electrode, most are all are used instead of GC electrode. I guess, is there any benefit we change working electrode?
If you change the working electrode.
If.
Why is BDD important for ammonia oxidation? Yeah.
Interesting.
Boron doped diamond has a wider potential window than glassy carbon, if I'm not mistaken, right? Yeah. It's like more inert, like it's more background. So like when you do a CV, for instance, of glassy carbon, which is like the natural comparison, right? With BDD. So when you do a CV on glassy carbon, so I'll do glassy carbon, a background CV, you might get like, I should draw it more so I can compare. Like whatever limits you're going to do, you're going to get mostly just background until you get to the extreme ends where you have, oxygen evolution and then hydrogen evolution. On something like BDD, you'll get like, is the capacitance is lower or higher? Is it lower?
It's a bit lower.
It's lower. Yeah. I was going to draw.
It's very it's like very thin,
it's thinner. Yeah.
Typically
thinner and wider.
Thinner and wider.
Yeah. It's sometimes used because it's like a better substrate. So it'll do oxygen evolution like later, like it's less reactive, and its capacitive window will be like thinner. So yeah, I should have drawn the glassy carbon one bigger, so I'd have a bigger comparison. It's a little trickier. And then it like won't do the hydrogen evolution until a little bit later or whatever. These are all like not perfect, but roughly speaking, this is kind of the idea. So for example, if you have a reaction that takes place like here or here, glassy carbon won't work too well because it's like already doing oxygen evolution or hydrogen evolution. But like BDD might be good because it's still sort of background current or whatever. And then if you have like small peaks going on or whatever, in your CV, like the glassy carbon is adding more of its own background current and the BDD is adding less. So some of those are kind of the idea. Now, as it relates to ammonia oxidation specifically, I don't know. I don't have a lot of experience with ammonia oxidation specifically, what potential it happens at, whether it needs more or less background current, or it's how heavily affected it is by those things. But what I've told you is my knowledge of why BDD is used in place of glassy carbon, for instance. And so I would assume some or all of what I just mentioned play into why it's, I guess, preferred for ammonia oxidation. But I don't know a lot more specifically than that.
Yeah. Okay. All right. I think that's all the questions that we've gotten. We have
some saved ones we've been trying to get
Yes.
to. So let's do that.
Yeah. Okay.
What do we have here first?
That's a good
Do you
question.
want to talk about potential or pulse height?
Yeah, either one of those. Yeah.
Actually, let's clear this one about impedance. So Lino Skako had asked a question, I think last week.
Yeah, last week.
I was out last week. Or the week before, anyway, whatever it was. But had asked, can you explain time domain impedance measurement, how it differs from traditional frequency scan EIS and how it's used? So I think that all I wanted to say, you actually basically answered this from what I can remember. All I can kind of add, I guess, if anything, is that impedance by definition requires three conditions: linearity, causality, and stability. And a time variance is a fundamental violation of the stability condition. So this is a semantic argument. And I do understand and recognize and have talked with people who do experiments that are like this. If it's the same, I'm not sure if it's the same thing, like time domain impedance. Some people have called it like non-linear impedance, or some people, there's different names for variants of this kind of experiment, from what I understand. I have a sort of fundamental problem or disagreement with their existence. Because, and part of it might be semantic, which is fine. Because if you want to do an experiment where you apply some sort of waveform over time, and that's all normal and fine. It's just, it's the application of the word impedance. It's not fundamentally impedance if it's not stable. And a lack of steady state, because you are allowing time variance, necessitates that it is not impedance. That word ought not to be used. And so my opinion, and based on these criteria, is that the analyses that come with an impedance data set are not appropriate. Like all of the sorts of analyses that require impedance data to be collected cannot really be applied, I guess, in my opinion. I know some people have different kinds of analyses and they do these for different reasons, perhaps, but I have some real sort of philosophical problems with this. It's just, if it's not stable, which means it's changing over time, there's a time variance with your experiment. It's just not physically impedance. It just isn't. Definitionally, there's no other answer, that it's just not definitionally impedance. So how it differs from traditional impedance is that it isn't impedance. So that's my answer.
This was a question. We can now get rid of that one.
Yeah, I was just removing it too.
Yeah.
We double removed it.
I think I did want to answer, or at least comment on this one, because this was a YouTube comment from, or this is a question from, I think, almost 2 weeks ago that I didn't have a chance to talk about. So this was with respect to square wave voltammetry and describing what exactly is pulse height, as well as sometimes papers will refer to it as millivolts PP, which is, I think it's millivolts peak to peak. And what does it affect, and what does it mean? That does it either increase or either oxidation or reduction of the analyte? Now, I'm still learning a lot about square wave voltammetry and the math behind it. It's somewhat convoluted because they always present things as dimensionless, whatever. But the neat thing about square wave, and I'm going to hopefully be able to share. Let's see. So this is the one reason why it's hard to kind of talk about this. Is it's like, all right, you have to actually draw, and like I can't type out what does this peak mean. And so what I believe, and I think, is my mouse showing up? Okay,
it is. Yeah.
So
it's a little hard to see, but anyway, we can see it.
I think what I mean by peak to peak is like from this step, from this pulse to the next pulse, is, I believe, the peak-to-peak millivolt change. There's kind of two things that are changing. There is, or not two things that are changing, but there's this height, this pulse height. It's being held for a period, and usually this period and this period, when it's stepped down, are the same. But then it increases by a very small increment, like it increases by this incremental, like small amount. So, um, so peak to peak usually is referring to one of these two things, and I believe it's referring to this small change. It's like, oh, it goes up, it makes a small change when it's pulsing, and that's I believe what it's meant. It could be the other one, but at the end of the day, there's really like three variables, if you will, that you can control with square wave. You can control like the amplitude, like this amplitude. You can control the step amplitude, and you can control the distance, the period, if you will. And there's a lot of equations. This is actually from one of our support articles on square wave voltammetry. And there's actually a bunch of equations that describe, this describes the technique in more detail, but also some of the equations that are used, because you can actually determine some very interesting things. I believe you can determine the, um, I believe it's the ratio of the diffusion coefficients for the forwards and the backwards reaction. I don't know if we actually have it here in this particular article. Yeah, that equation's not here, but yeah, that's what it means. Let me look at what the other parts of the question are. When you change, when you're stepping the potential up and down, you're oxidizing it, and then you're reducing it, you're oxidizing it, you're reducing it, but you're measuring difference currents effectively as you do this experiment. You're always taking a difference between, let's see, there's this one equation. You're looking at a difference current, and really it's like, difference between the forward and the reverse current. And you're able to get this kind of dimensionless peak current parameter that can be used to make further calculations of things. But it's manipulation of this that allows you to determine things like the diffusion coefficient, the period, and then the peak height by adjusting some of these parameters. So I just wanted to at least talk a little bit about that, like what is meant by the pulse height. Well, it's those parameters. Okay, all right. So I wanted to at least mention that. I'm going to now remove that from the list and then stop sharing. Okay. Do we have any more new questions?
There's one question about a couple of different plots that can be made. I can talk about.
Yeah.
So Mohammed had asked, what is the benefit to draw the two diagrams, log of scan rate versus potential, and also scan rate to the 1/2 versus current density? So first of all, I'm not sure log of scan rate versus potential. I'm not sure what that is for. What am I missing? Can't think of it.
Unless he's talking about
log of scan rate versus potential. What is that?
Unless he's talking about the trumpet plot, and instead of plotting it versus the scan rate, you plot as the log of the scan rate.
Yeah,
that's maybe the only one I can.
If you're increasing, so one of the ways that would matter is that if your scan rate is like going from 0.01, volts per second up to multiple volts per second, like you're spanning a huge range,
which you probably are.
Yeah, exactly. Then plotting it as a log can help space the points out more easily. This is why like impedance data is plotted logarithmically, because you're going from like 0.01 hertz to 100,000 hertz. It's like many decades, right? And so you can plot it linearly. It's just it's terrible to look at, So that's one of the reasons. But from a analysis perspective, I'm not sure that I don't know what plot that where that is plotted that way. I'm not sure I know like log of scan rate versus potential. I don't know what that signal is from. But the second one is pretty common. Scan rate to the 1/2 versus current density. That's basically what a Kentucky-Levitch plot or a Levitch plot. Which one? Either?
No, the Randles-Sevcich.
Randles-Sevcich equation?
Because you're looking at scan rate, not rotation rate, right?
Oh, right. Scan. Yeah. Sorry.
Yeah.
Right, yeah. Scan. Yeah. Randles-Sevcich equation. So yeah, I was gonna. You probably have that. Don't we have it?
Yeah, we have that. That should be
useful equations somewhere in here.
Should be in the useful equations.
Pull that up right here. Yeah. Where is it?
Let's see.
That's one of these slides, right?
Tafel, Butler.
There it
There we
is.
go.
Yeah. So like current density, it's probably the other way around. It's probably current density versus scan rate to the 1/2. But
Yeah.
the second equation you see here,
Room
IP is equal to 2.69, blah, blah, blah. NaC, and then it looks like whatever V, but it's new.
Yeah,
or
new.
or epsilon, whatever people use. So I've had an argument with my colleague about
Yeah,
that. He's insistent it's epsilon, and I don't care. So anyway, but I digress here. Point being that when you plot IP versus the square root of scan rate, you can see what's left over. 2.69 times 10 to the minus 5, n to the 3/2, A, C, and there you go, D to the 1/2. So basically what it allows you to do is get an estimate for D, for the diffusion coefficients. You typically know the number of electrons transferred, you know the area of your electrode, and you know the concentration of the electrolyte you're using. So you make that plot as a means to extract the diffusion coefficient. So that's the answer. That's why that's done. Again, the other one, I don't know that I don't know what log of scan rate. The only thing I think of in general is that, again, one of two things, what we just said, which is that you're doing a bunch of scan rates, and the logarithmic plotting just helps visualize them a little bit more easily. The other is that you can plot scan rate to the 1/2 or to the minus 1/2 or whatever, and that's what appears in like the Randles-Sevcik equation or maybe some other different equations that are functions of scan rate. Taking the logarithm of a number with an exponent is just another common way of simplifying things, right? I mean, mathematically, the logarithm of a to the n is the n comes as a coefficient, right? I'm hopefully not saying anything you don't know, but I'm just pointing out that it may be, if you're finding a logarithm of scan rate or a logarithm of something in a plot, it's just a simplification because the exponent becomes a coefficient and it's just easier to manipulate that way. So that might just be a mathematical thing. That's all I can think about.
Yeah. I think it's probably for the trumpet plots, because people end up going to very, very high scan rates and very low scan rates to look at it. But
I think you can talk about this pretty well because you've made this discussion about Butler-Volmer and things like that. So Dooley's is back here to talk about the foot of wave. But basically, can you explain the role of overpotential on the foot of wave analysis? I think I was confused before because the overpotential at the foot of the wave is way less than the E1/2. That's correct. So it's a common misconception that, for example, no oxidation occurs until you are greater than the E0 or at E1/2, right? It happens before then. And so the foot of the wave or the onset potential, whatever terminology here, indeed, it is before the E0 or the E1/2 occurs. You've talked about this before. So like Butler-Volmer kinetics, it's like the current increases. Like we tend to say, and I say I'm guilty of this all the time, where it's like oxidation does not happen until you get greater than E0. It's not technically true.
Yeah, it's
right?
So if you look at just like a CV, just I guess any CV, let's look at this, and maybe using Math Live is a better way to do this. But I guess I'm still trying to understand the question a little bit more. But you have your, I'm just going to kind of draw it exaggerated, just so that we have some space. But we would say something along like somewhere in the middle here is the E naught. But he's talking about E1/2. He's talking about like halfway up this. He's talking about like halfway up this potential here.
No. So E1/2 is E naught. E1/2 is halfway between the anodic and the cathodic peaks. My understanding of what he's talking about. So draw a more normal CV without exaggeration. Because I think, or I can draw a regular CV. And this is my interpretation of what he's asking. So if you draw like a regular looking
CV, as regular as I can draw,
right?
God,
so so close.
I can't
actually. Here, I'll do one better. Don't draw. All right, because drawing is hard for both of us.
I'll stop sharing.
Let me share. Hang on. I got you.
You can also just.
I have actual Ruhex CVs right here that are nice and perfect.
Yeah. Okay.
So my impression, Dooley's, please correct me if this is not precisely what you're talking about, but I think I've got it. What I believe he's saying, the E1/2 of this, I'm going to try. So here's that's the peak. Up here is the oxidation peak. Here is the reduction peak. So halfway between in this box that I'm drawing arbitrarily is the E1/2, which is roughly the E0.
Yeah.
Right?
For Ruhex, yes.
Now, forget about it, right. So it's like here.
Yeah.
It's this is E1/2, whatever, in this range.
Okay.
The foot of the wave is right here.
Yes.
So he's saying that right here at minus 320, whatever, this is where it starts, the onset potential. That's less than E1/2. E1/2 is here.
Yeah.
The foot of the wave is here.
Yes.
So why are they different?
Why are they different?
In other words, why do I have any oxidation uptick in the current before I've hit E0?
Oh, yeah, okay. Because like overpotential is also, because overpotential because he's using the word overpotential.
Yeah.
And sometimes I think about overpotential.
So the foot of, so to be clear, and that by that extension, this is E0 right here.
Yes. Oh,
so the foot of the wave has a negative overpotential.
Yeah. Okay. Yeah.
So why is it oxidizing at all?
Yeah. Why?
I just wanted to set you up because you've explained this well before.
Yeah. So
yeah.
Oh, it just goes back to the Nernst equation.
It's always the Nernst
equation. It always just goes back to the Nernst equation, which is, and if you think about it, it's like, oh, does electron transfer? So I guess this question is like, okay, why is there any current flowing at all? So there's the Butler-Volmer equation that's describing, you're looking at the change in the concentration at different potentials. And current will flow to, or if you want to even think of it this way, you have the Nernst equation. And then if you're at different potentials, that relates to a different ratio of concentrations. Because it's at equilibrium and the kinetics are fast, so you establish equilibrium very quickly. Whenever the potential changes, there's going to be a change in the ratio of concentrations. That's going to result in a current flow. And so even if you're away from the E0 of the reaction still has some value where like, oh, at equilibrium, this needs to be the ratio of the concentrations. If I'm at this point, I am no longer at that correct ratio. Current flows, it corrects the ratio. And then as you keep moving, it keeps correcting. And so that is why that's why you see current flow. That's why the potential where the foot of the wave analysis occurs is much farther away. And I mean, much farther away depends on the kinetics of your system. If your rate constant's very slow, yeah, it's going to be super, super far away. But if it's very fast, it's actually like in Neil's example with ruthenium hexamine, it was maybe like 50, 100 millivolts away. That's it. But it could be a lot farther away if your rate constant is slow. Another way, if you want to get even like more deep into like why fundamentally does this happen? Energetically, if you think about a gas phase molecule, for example, a gas phase molecule has discrete energy levels, right? We know about that. But when a molecule is solvated, per se, for an electron transfer, when it's solvated, it actually has a distribution of energy states. So you have a density of states for the oxidized and the reduced species. And so that's why you actually can get current to flow at a potential that's not a discrete value. That's not the exact E0, right? So when it's not exactly E0, there's still an energy state that the molecule can accept or gain that electron transfer because of solvation energy and its orientation. But if you tried to do this experiment in the gas phase, your CVs would be sharp peaks that just have to do with like the ionization energy of like ionizing, going from ruthenium 2+ to ruthenium 3+.
Gas phase CV sounds amazing.
Oh yeah, I mean it's probably a thing. Well, all I'm saying is if you did an ionization reaction, which is what we're basically doing in electrochemistry, or an electron transfer, in the gas phase, it would be at a discrete point. But because we're in solution, we have a we have a distribution. You have a whole cyclic voltammogram of like, hey, we're at all these potentials, current is flowing, which means electrons are being transferred at potentials that are not exactly E naught. So that's another like deeper level if you want to understand what's happening.
Yeah.
Okay. That's my tirade. What is let's see, do we want
Naresh
to
has downloaded Aftermath. I can just mention.
Uh-huh.
I assume Naresh, you've downloaded it from our website. So yeah, our software can be downloaded from our website for free, but many of the features we will need a license for. So if it's asking you for a license, what do you do? Well, you can purchase a license, or you can use it without a license. I believe it. You can.
Yeah, you can still
You can
import
still
data.
import data. Yeah, exactly. Like you can create a new archive, add a new plot, and copy and paste data into it and do some of the analyses that I showed today. You can't do EIS circuit fitting or similar or electrochemical simulation. Those require a license. We sell licenses for those. You can find those on our website as well if you wanted to purchase those, or you can reach out to us on our website. We can sell some of those licenses. But also the other reason it's asking for a license is that, of course, our software is used to control our potentiostats. And so if you just download the software and open it, it's probably wondering if you have a Pine potentiostat. And so it's looking for that license. So when you purchase a Pine potentiostat, we supply the license files for the potentiostat, and that obviously allows you to do experiments. And to that point, Anderson says, congrats for the free lecture. We appreciate it. Appreciate you watching. What would be the main parameters regarding to choose a potentiostat or galvanostat? So the number one is it made by Pine? Right? That's a yes, no Boolean. So if the answer is no, you don't buy it. No, I'm just kidding. Yeah. So honestly,
Depends what you're doing.
Yeah, of course, right. So the main things, I mean, potential and current limits are like the most fundamental thing to be looking at. So if you're doing things like small scale, solution phase electrochemistry on small electrodes, disc electrodes, things of that nature, the currents you're looking at are probably in the milliamp microamp range, right? So if you have a potentiostat that gives you a few hundred milliamps to an amp or something, that's probably more than sufficient. Hundreds of milliamps is probably enough as well. Some smaller form potentiostats, for instance. If you're doing aqueous or non-aqueous, like solution phase systems, you're looking at plus or minus 1 to 2 to 3 volts, whatever in that range. So any potentiostat that has 4, 5, 6, 7 volts in that range is probably sufficient. So those are the first kind of general things to be looking at. Then honestly, it's like other more advanced features, right? Does it do impedance or not? Do you need impedance? Do you not need impedance? Do you need IR compensation? Do you not need IR compensation? Not all potentiostats can do that. And then, there's a lot of other things like the software, and sometimes it's just a preference, of course, but how important is the software? We were just talking about this earlier, actually. It's kind of funny, right? So how important is the software to you, right? Do you care if the software is user-friendly? Does it just have to be functional and work? It depends on what your mindset is. If you're more of an analytical scientist, you might care more about the, software looking and being user-friendly. If you're maybe more engineering minded, you might care less about how it looks and just more that it functions. So it kind of depends on maybe your personality and perhaps your discipline. And so there's some of those kinds of things. And then, how well it allows you to do what you're looking to do. Because if you're looking to do just a couple of CVs, something very, very simple and maybe perhaps less expensive will work. If you're looking to do pretty complicated scripting and a lot of, triggering and sequences of experiments, you might need something a little more sophisticated, or at least a software program that allows you to do some of those fancy things, I guess. But that's just a general overview, I guess, for you. Do you have anything to add? I don't know.
Oh yeah, I think you covered all the major points. I think honestly, one thing that I think Neil can attest to this. One thing that we hear a lot of people talk about is like data management.
Oh yeah.
It's like people are being able to perform and automate tons and tons of experiments, generate tons and tons of data, and write scripts. So being able to export your data in an easy manner that allows you to analyze it is also an important feature.
Yeah, for sure.
So that's one thing I hear a lot about. And really, it depends on the experiment. Sometimes people are doing crazy wild sequences of experiments with like weird time resolution. So those are
Yeah.
other things that and like if you're doing like very low current experiments, you need a current range. Like we're talking about the high end current range, but some people are doing
Yeah,
like
that's a good point.
nano and picoamp resolution stuff, and so that's like the other extreme,
Yeah.
so to say. So it depends, but those are all the main parameters. I think Neil gave all the major ones, and of course, I guess price, like
Well, price.
how expensive is it?
Yeah.
Do you like the is the customer support good? Yeah,
Do
some
they do
people
free live
do
streams where
they
they
do.
talk about these things?
Yeah,
Those are just some of
that's
the
another
things.
yes no. Like
Exactly.
if they don't do that,
You don't want to buy it.
yeah,
Yeah, exactly.
yeah, that's rough.
Look, you asked the question to a couple of guys that work at a potentiostat company. You have
Yeah.
to expect a little bit of that. But yeah.
Yeah.
So hopefully that's a decent overview for you, Anderson. There's definitely a lot of factors to consider, and at the end of the day,
Yeah, I
whatever's
wrote
kind of most important to you.
I
So.
wrote an article a while
Yeah, you did
ago.
about choosing a potentiostat.
Yeah.
It's probably locked in our old KB though.
Well, no, Tim moved all of the posts into an archive
Oh, so we have
space.
them. Yeah, we just updated our website. So this is some insider baseball here, but we just updated our website, which, if I may be so bold, our colleague Tim what essentially did himself, and it's incredible. So our new website is new and fancy, and it looks really great, and it's really nice and easy to navigate and the whole thing. And Tim worked extremely hard over a long period of time uh, to do this. And so if you like our new website, give Tim some love.
Yeah.
He did an excellent job with this.
Yeah.
So anyway, yeah,
I
this
read
is
a
our
bunch of
old.
random
We had a
stuff.
bunch of, as with everything, we literally launched it on
Mhm.
Monday, so it's
Yeah.
brand new. We've been
brand
working
new.
through a million bugs, and Tim has also worked his butt off to get all these bugs ironed out, and it's
He does it
amazing.
very fast too.
Yeah, it's
actually
incredible.
incredible.
He really is quite incredible. So, but as these things happen, we had old content and anyway, yeah. This is one of the old articles I guess you wrote about.
Yeah, I
choosing
wrote it a
potentiostat.
while ago.
Yeah.
Like 2020 or something.
Yeah, it's been a while.
How to choose a potentiostat. So, but yeah, that might be helpful. It goes into some of the weird, because more specifically, it goes into how do you interpret like the spec sheet on a potentiostat.
Yeah.
Sorry. So, and some of those things like, what was it, like common mode? Yeah, there was like something about like common mode that I'm like, what is common mode? Or like electrometer specifications. Like, what is the electrometer? Now we know a lot more about what an electrometer is, but like, what does it mean when you see an electrometer has got like 10 to the 15 ohm impedance? Well, what does that mean? So that this kind of helps a little bit with that, understanding those things. So I think those are the questions that we have thus far. There are
Do a couple of circuit fitting things here.
yeah, maybe we just finish with the circuit fitting because it's
I think that's
2:47.
yeah.
right
We'll
now.
try to wrap up here. So if there are questions, feel free to ask them.
Yeah.
But there were a couple of people who last week. Last week.
Yeah. Last week
had some
sent some data
to
us.
you. Yeah. So the first was Meliodas,
Mhm.
who this person had some data with, I guess, iron, 4 molar KOH.
Yeah.
So I have already loaded that in. Let me find which one it is. I think is it this one? It's this one. Okay. Let me share my screen. So this was some data. I mean, essentially the question, if you will, was just about helping doing the circuit fit of this, right? And let me share my screen. Okay. And the data looked like this, apparently, assuming I've imported it properly, which I think I have. And so the data, so some of the question was related to this. Well, I don't know, maybe not. There was a bit of a high frequency kind of a
Yeah, help circuit fit this. That was it.
Right. Okay. So there's a high frequency tail here, a little bit of inductive artifact, which is just negligible. There's kind of what appears to be a high frequency, a little bit of there's a bit of an inflection here, and then it kind of looks simple. I mean, actually, funny enough, it looks almost like there isn't much going on. Like when you zoom out, you can kind of see, this is my sort of professional interpretation, I guess I'd say. It kind of looks like, well, it's like one semicircle. It's almost like, is there an inflection here? Is there an inflection here? It's actually hard to tell. which makes it interesting. But the first thing to do always is Kramers-Kronig. So this is like an analysis to make sure, is it accurate impedance data in the first place? And roughly speaking, it is. There's a little bit of deviation at that low frequency point. So that will come into play a little bit later when I do the fit, and I'll show you, which is normal. It's pretty normal to have some drift and some deviation at low frequency. But overall, obviously, error statistics is pretty low, and you can see that the results fit pretty well. So the long and short is that this is relatively, I would say, accurate impedance data. We should proceed with circuit analysis. Now, I'm going to just jump to the conclusion because actually, I'll do one fit and then jump to the conclusion. So the first sort of obvious answer you might pick would be like 2 RC units, because you can it kind of looks like them here, but there's a dip here, maybe even at higher frequencies. But as a quick analysis, you might assume there's 2 charge transfer processes. I could fit 2 void elements, and I might pick this circuit to try my fit. Okay. And so the first thing that I'm going to do actually before I proceed any further is just exclude the high frequency artifact kind of stuff. So about to here, I don't really need these data points. That's if I zoom in on the Nyquist plot, I'm just getting rid of this little tail. I don't need to fit that. It's not anything real. Okay. Now I can get a very quick, just quick and dirty here, an estimate of my fit here. I might have to mess with some of the min and maxes, but I'll just kind of, so it's not terrible is my first general opinion here. Okay. I can increase this one a little bit. I think that might help ever so slightly. Maybe that'll help. Yeah, a little bit. All right. Not terrible results here. 0.13. That's the chi-squared. I'll compare that to other chi-squareds. We'll see how that works. You can see there's deviation at the low frequencies. It doesn't quite fit. You can see the phase angle kind of navigates through. There's more dips in the fit data than the actual data. It's not terrible. It's not perfect. I can do unity. The end fits great. The beginning fits terribly. This error statistic is much worse. I'm going to go back to what I had before. All right. So anyway, this is just like a first. Maybe this is a fit. It's close. Maybe it's not the right fit. So Alex actually had the idea. What about a Gerscher element? Now, I won't do all the fits because just for time. We tried doing a few different fits.
Yeah.
You and I, earlier in the week. Warburg short. It may still be a possibility for a Warburg, like a finite element Warburg could fit. Could be the answer. It allows you to extract like a diffusion coefficient and diffusion layer thickness and things like that. It didn't fit quite so well, but the Gerscher element, strangely enough, actually does fit pretty well. And so I'm actually going to jump to the end fit, so I don't have to tinker and kind of again waste more time here. Well, not waste, but anyway, playing with the circuit fit can take a little bit of time. So this is the Gerscher fit. So what I've done, I'll bring up the circuit so you can see here. I drew this circuit custom. So this is a leading resistor here, and then there's a 1 RQ element here, and then I have like a Randles circuit, but with a Gerscher instead of a Warburg. Now, a Gerscher element is a special kind of an element that combines a chemical step with an electrochemical step. So the full caveat here is that I have no idea if this is appropriate. Okay, this is this person's data, right? I'm about to erase the fit and mess it up on purpose here. Anyway, I was just showing the circuit, but now I've reversed the fit. Anyway, you saw that it fit pretty closely, which was really pretty good. And the error statistic was 0.02. So it was like 2 orders of magnitude lower or 1 order of magnitude lower than the Randles or RC fits. And the long and short here is that I don't know if this is appropriate, but it does seem to fit pretty well, which again suggests that maybe we have like an electrochemical and a chemical step occurring. And one of the fit parameters of the Gerscher element is this K. So you can see this K, and again, I know the fit doesn't fit anymore like it did before, so I could tinker with the values and get it to fit like it did last time. The main message, though, is that I'm able to get a first order rate constant, kinetic rate constant K, as part of the impedance fit, which is kind of neat because I'm able to get a little bit of chemical kinetics from electrochemical data, if in fact that is what's happening here. So that was just possibility, just from the perspective that with no other knowledge, let's just say Alex and I looking at these data, maybe the Gerscher is an appropriate way to fit this because it fits quite quite nicely, if it's much better than the other elements did. And so that was just one suggestion, I suppose, if this person, thinks about that.
Yeah.
And then I guess there's a few other questions.
Yeah, a few other
Probably
questions
should
we
move
may
on. We'll
wanna.
skip the other one for now. We'll try to
Yeah,
get to these
which
questions.
this is fine.
Yeah, no problem.
So Zabah has a question. He wants to know how in the potentiostat does the voltage go into the working electrode, and then just I guess more specifically, how does the voltage go into the working electrode and the potentiostat after completing the feedback loop? So we'll go over this very quickly. There's a full video on how potentiostat works, but this is the kind of simplified potentiostat circuit. And when you set the potential here at the potentiostat set point, it goes into the inverting input of a high gain operational amplifier, and it pushes voltage, or more specifically current, through the counter electrode. And when you tell the potentiostat apply +1 volt versus ref, we use an operational amplifier called an electrometer with a gain of 1 to measure the difference between these two, the potential difference between these two. And so current flows through the counter electrode between the counter to the working. And so the way the working electrode potential is determined is actually through driving the counter electrode. So that's what happens. So when the potentiostat is set to like +1 volt versus the reference electrode, the counter electrode drives current through the solution to the working drive electrode here, such that the potential here changes with respect to reference until it equals +1 volt. So that is fundamentally how the working electrode potential is set to 1 volt. Now, once it's at 1 volt and nothing else happens, then no more current is going to flow. But then once this deviates ever so slightly, the potentiostat will apply a little bit more current, a little bit less current, until this thing is 1. And this happens very, very quickly. This is happening many times. That's the kind of the frequency of feedback, if you will, for this circuit. But in the interest of time, I just wanted to quickly describe that that process to you, because I think that's ultimately what you're interested in. And then there's one question from Tayab, who's asking, he's doing open circuit potential versus time analysis for the first time, and in the CH Instruments 3 electrode system, he's using that, but his knowledge is that OCP is calculated by removing the counter electrode. You can keep the counter electrode in, but the open circuit potential is only measured between the working and the reference electrode in a 3 electrode system. So whether it's in the solution or not, it wouldn't matter.
The key here is when the potentiostat is removing the counter electrode in its circuitry is what's happening. You don't have to remove it yourself. So like, I don't know if that's physically what's happening in a CH instrument, for example. That's not our company. I don't exactly know what they are doing physically, but one of the ways in which a potentiostat, for example, you can imagine like there's counter electrode, working electrode, and reference electrode connected into the instrument. Well, as part of the OCP measurement, the potentiostat just like cuts off the counter electrode connection. Like there's a switch and it like opens the switch. That's probably not exactly what's happening, but you can just imagine that's effectively what's happening. So the removing of the counter electrode is something that happens with the instrument itself, but that doesn't mean you have to physically disconnect the counter electrode. Now you could probably do a thing where you actually disconnect the counter electrode and measure OCP and see what happens. It's probably going to be the same. It should be the same.
Yeah, it should be the same.
If it isn't, I don't know what the heck your potentiostat's doing. But,
yeah, that's
but effectively that is what's happening. But you don't need to disconnect the counter electrode. You shouldn't have to anyway. It should happen automatically. So, but so that is fundamentally what is occurring, I believe. So,
I think that's it. That's all we can really.
Well, book for electrochemistry, Barden Faulkner.
Yeah. Electrochemical methods.
Yeah. The famous Barden Faulkner book.
Yeah. Fundamentals and applications. Yeah. If you just type in BARD electrochemistry, you'll probably find
Mhm.
the book. Let's
Yeah.
actually see if I'm right. Bard electrochemistry. Yeah, the second edition of the book comes up first, and there's a third edition
Mm.
that's out. So you'll be able to find it.
Yeah. Electrochemical methods. This last question, Saktipada, I think you're at IIT Bombay. You're looking to use our software for simulation. So all of the data plotting and things like that is part of you can use in our software. You can import files. So if you can get from your auto lab or from biologic, usually you can get CSV or like XY data, right? You can copy and paste directly into our software. Our software can't open a Nova file or an EC Lab file, for instance, but it can get XY data and copy and paste it into the software. So um, that's not there. So I'll try to show you very briefly. That's not it. I want to do. So for instance, I'll just kind of show you a thing. Not that. So
Arnab Dutta is
so okay,
Do
interesting. Yeah, so Dr. Dutta, I think that you probably have our equipment, but not our potentiostats. I think Dr. Dutta has one of our rotators possibly. So, but anyway, the next time I'm in Mumbai, I may visit you. I haven't visited in a few years, but I've been to IIT Bombay like 4 or 5 times in the past years, and it's been several years since I've been. But I will be visiting again at some point. So the next time I am there, I will hopefully meet you in person. But importing data, for instance, you can create a new archive, create a new plot, and then if you have the like CSV data, like XY data here, you can copy it and then just paste it directly into here. You can pick your units, membrane specific resistance and molar volume, whatever, it doesn't matter. You can pick whatever units. I just picked random units, right? And then put your data into ours. So then you can do baseline tools, and that's a funny slope. Molar volume against membrane specific resistance. So you can see you can add all kinds of SI units in here, and it respects the units. It is what it is. I don't know what these units mean, but anyway, that's possible. As it relates to simulation or circuit fitting or those kinds of things that I showed today, those require a license. Yeah, you have the RRDE. Yeah, I believe we've sold some of those to your lab. So Dr. Manoj Nirgat has some of our equipment as well as our potentiostats. He's in chemical engineering, I think, not chemistry. I'm not sure which department precisely. And then Arindam Sarkar has some of our equipment as well. And I don't know if he has potentiostats or RDEs. We have a lot of RDEs at IITB. I don't know how many potentiostats. Again, Dr. Nirgat has some. So there are some Pine equipment as well around IITB. But the simulation software and the circuit fitting are licenses that you can purchase, but they're not free. So if you do want to do our software and some of those analyses, apart from your other potentiostats, those are licenses we can sell to you, but they're not for free. So I think we can end it there.
Okay. All right.
Yeah. Chemistry department. Okay. Yeah. So yeah, so there's chemistry, there's chemical engineering. Some of the professors who are using them are different ones. Okay. So
we're about out of time right now. We usually try to just do this for 2 hours. So but we can save questions for
Ziba, we can answer your question I think next week.
Yeah.
Is the plan here. We are about out of our time. But that's one that we can definitely answer.
Yeah. I'll add those. I'll add that now.
Perfect. Okay. So yeah, we'll call it here. And there's another question I think we can add there. Of course. No, apologies for those who are showing up now. We're at the end of our live stream, so we always try to make sure we get to everybody's question, and we will queue them up for next week. We do this every week at the same time, which is 1 to 3 p.m. Eastern time on Fridays. So for different time zones, of course, that's different for everybody. But we will have to catch you next week for the follow up of these questions. But we do appreciate everybody's time and attention and questions. As always, we didn't even get to all of what we wanted to get to, as we tended to be. But we do appreciate everybody very much. And I hope everybody has a good weekend and rest of Friday, or if it's already Saturday for you, whatever.
Yeah, that's right.
I think it's Saturday for some people. So
yeah.
Anyway, thank you, everybody,
All right.
and take care.
Bye.